Dear students, today we are going to discuss a new topic, Shunt Shunt feedback circuit. So that is a continuation to the last lecture, Transresistance amplifier. The other name is Transresistance amplifier. Your input will be for Transresistance amplifier. Your input will be current and output will be voltage. So it's a EZF. Z, that is a determination for this trans resistance. Already we discussed in the earlier classes. Trans conductance means you will be having a G, and voltage amplifier means V, and current amplifier means I. Here it is a trans resistance, so Z. So A Z equal to your output voltage divided by input current. Okay. So here shunt feedback. I will say why it was said to be the shunt feedback by looking the circuit. Okay, so we will discuss in the circuit. So your sampling here you want to understand sampling is your sampling pot is your shunt. Okay, sampling pot is a shunt, and mixing part is also shunt. Right. So this is a two thing you want to remember. Okay. So let me go to the circuit. See, in the circuit, I will explain why it was said to be the shunt shunt. See, here this is your output. This is a common source circuit, source, gate, drain. I am taking the output at the drain. Your feedback is connected from the drain. So both are at the same terminal. So it should be a shunt. So shunt, I can write it as a voltage. Look at observe the circuit clearly. The feedback which is connected to the input directly to the gate. So that means it should be there is a mixing part. Mixing part will be a shunt. So that means voltage shunt feedback circuit. Okay. So by looking the circuit, you can identify easily. This is a shortcut method to identify any circuit. This will be very useful by understanding the concept clearly. Okay, so this circuit is coming under the voltage shunt feedback. That is shunt or trans resistance amplifier. Your output will be voltage and input will be current. Okay, I hope you understood. Let me go for this problem statement. So the threshold voltage is given to be a 0.4, and your conduction parameter 0.5, and quotient current I want to find, and you want to find small signal transistor parameter 2, and trans resistance amplifier transfer function, that is V naught by Is, and finally output impedance we want to find, that is the resistance. Okay, so first we'll start the DC analysis parameter. So to find the DC analysis parameter, first I'll start with the VGS. To find a VGS, I want to apply the KVL in this part. Okay. So when you apply the KVL in this path, you want to remember the MOSFET gate current is 0. So right, so that means you will not take this RF because the current in the gate will be 0. So once you apply the KVL to this, what you will get? V plus minus of IDRD minus 0 minus VGS equal to 0. So when you rewrite this equation, you will be getting this equation, right? I hope you understood. You know this basic equation, ID equal to Kn VGS minus VTN whole square, right? So here I want to substitute this ID in the equation, the above equation. So you will be getting V equal to Kn VGS minus VTN whole square RD plus VGS. Now I will plug in all given values, that is known values. The V plus is 3 and Kn 0.5 and RD 5 and VGS minus VTN is 0.4 whole square plus VGS. You expand this with A minus B whole square formula. So once you expand, you will be getting 3 equal to 2.5 B square GS plus 0.16, that is B square minus 2AB plus VGS. Now you multiply all term with this 2.5, you'll be getting 3 equal to 2.5 V square GS plus zero point 0.4 minus 2 VGS plus VGS. When you rearrange the term, subsequently, you'll be getting 2.5 V square GS minus VGS minus 2.6. So, by using quadratic equation, by using the quadratic equation, you want to solve this equation, you will be getting two values, that is VGS, that is unknown value, one value will be, I solved by using the quadratic equation, one value will be minus 0.83 and another will be 1.239. So we should take only the positive VGS because it is a n channel MOSFET, right? So this one we should avoid. Okay, this one you should not consider, and I'm taking only this another value, that is 1.239. This is very simple. You know, A value will be 2.5 and B value will be minus 1 and C value will be minus 2.6. You know the quadratic equation, just plug in, you will be getting your VGS, or even you can calculate with the calculator. Okay, that is for easy understanding, right? So here now you got a VGS. So now very simple to find what is your ID. So what will be ID equal to Kn VGS minus Vtn whole square. So Kn will be zero point 0.5 and VGS will be 1.23 minus zero point 0.4. So we'll be getting 0.344 milliamps. This is your drain current. So when you look at GM, so GM formula 2 square root of Kn ID. How you obtain this formula? I explained in the last lecture, right? The same procedure you have to use here. So 2 square root of Kn ID. So 2 square root of, that is zero point 0.5 into 0.344 will be getting 0.829. That is your transconductance. So this is your important to proceed the problem further. Now we want to find the small signal analysis. Okay, so this is very important. Okay, so let me first draw the uh, small signal circuit, right? So I'll let me draw the circuit which is given in the previous slide. So this is a given circuit for you, right? So gate and drain, and this is the source. I drawn in the simple manner. Okay, supply, and this is the ground. So when I draw the equivalent circuit, you can see the common terminal is a source. What is the input terminal? It's a gate. And output terminal is drain. Right? So here you will be having your VGS, and here it was a current. It was clearly said it was current. So current, you will be having current here. Right? That is and here in between a gate and drain, you can see the RF, the feedback resistor. Right here you have a resistor too. This RD. So RF. Then here you have a dependent current source. So in MOSFET always will be represented by using the rhombus shape. In BJT small signal analysis will be represented by circle. Right? So this will be GM VGS, that is a dependent current source. Then here you will be having your RD, that is a external resistance RD, and this is your output voltage. So our transfer function, output voltage divided by input current. Okay, so this is a simple procedure to draw the equivalent circuit. I hope you understood, right? So first I have drawn the common terminal, then I mark the gate, then drain, then I mark that VGS drop, then I have given the RF that is connected between gate and drain, that is RF. Then it is clearly mentioned the input is current source, so IS I have given here. IS or IA, it is up to you, only for our understanding. Then you have a current source, that is your drain current. drain current, you will be having GMVGS. Then circuit, you can see the RD is was given here. So when you draw the small signal model, so you know that you want to remove the DC and you want to connect all other passive elements to the ground. So I have done same. So RD is connected to the ground. You can see it was grounded, and I have taken the output from this section, right? So now let me clearly draw this circuit again. So for a clear understanding, I'll draw the small signal model again. Okay, so this is your common terminal source. This will be a gate, and this will be a drain. Here you have a feedback RF, and here you will be having your VS, and here you will be having your dependent current source GM VGS. Okay, so that is capitalized small d. RD is your output resistance, and here you will be having your V0, and input current will be IS, right? So this is your our understanding from the previous circuit what you have discussed on the main circuit. So now we want to find the transfer equation. We don't know what is the equation for this given problem, so we want to find. We can't write it directly because we have a RF resistor. So RF is connected between the output and input, so we want to derive it. So very simple. So first I'll be explaining the equation 1. So when you apply the KVL, sorry, when you apply the KCL, Kirchhoff current law, you can see here. So here all the current are leaving this branch, and this branch. So what you will be getting if you take any node, so all the current are leaving. So that means I can write corresponding this, you will be getting V naught by RD, that is V naught by RD, because this is a KCL, and the current term is GMVGS, right? So we are applying the Kirchhoff current law. So sum of the entering term is 0, sum of the leaving term is this 3 term. So one term, this is a 1, this is a second term, this is a second term, and third term is connected in between the drain and gate. So this is a, we are going from the like a left to, we are moving from this side, right? So that is V0 minus VGS divided by RF. So this is a V1 and V2 divided by RF. So we will be getting V0 minus VGS divided by RF equal to 0. So if you look at this second equation, so that is your source current. So this is, here we are looking from this side. So drop, this will be a first drop, VGS minus V0 divided by RF. See, when you find this side, you are seeing from this side, you are seeing from the output side part onwards, like this direction. But when you look at this, you are looking from this side. So we should take it as a first drop minus this second drop divided by this RF. So you will be getting this equation. This is the main equation to proceed further. I hope you understood. If you have any doubt, you can put in the comment box, right? So like when you expand this, rearrange VGS minus V0 equal to ISR, right? Then when you rearrange this equation, that is this equation, you will be getting VGS equal to ISR plus V0, right? So from this we have found that VGS equal to ISR plus V0. Let me take the equation number 1 and write like this. So separate these terms for my easy manipulation. V0 by RD. and gm vgs plus v naught by rf. I break this term, minus vgs by rf equal to 0, right? So here I have taken that v naught terms coefficient common, so you will be getting v naught. So you can see very simple steps. V naught will be getting 1 by rd plus 1 by rf. Then I have substituted vgs, that is this let me take it as a 4, this will be 3. So I have substituted 4 in this equation 1. So we'll be getting gm into isrf plus v naught. Similarly, I have substituted here VGS. So minus ISRF plus V naught divided by RF equal to 0. So I have taken this ISRF common. Then you will be getting GM minus 1 by RF equal to 0. Then I have multiply all terms, individual terms. You will be getting V naught by RD, V naught by RF plus GM ISRF plus V naught GM minus ISRF divided by RF minus V naught by RF. So then I will cancel the terms. So this term will be cancelled, plus minus. Then I will take a common v naught and v naught, it is common, so I will take, so 1 by rd plus gm. Then from here I can cancel r of r of, then we can take a common is gm r of minus 1. So when you rearrange the equation, right, I want to find like a v naught by is. So when you rearrange, so this is in plus, when you take to the right side it will become minus. So for polarity interchanging, I can write like a, that is 1 minus gm r of divided by 1 divided by rd plus gm. So this is a transfer function which you obtained here. So see, this one you want to find for individual circuit. This is a very important. You can't write directly from the basic equation, because here the transfer function is given, so we want to include those parts. With that consideration, we want to derive the new equation, but basic is same. So gm and rf I have substituted, I will just plug in, and rd gm I have substituted, and finally I got minus 19.23. so this minus generally define the, where you have a phase shift in your circuit, that is the input and output is phase shifted by 180 degree. Okay, so I hope you understood. So let me go for the next part. Okay, so the final part is we want to find the output impedance, right? So we'll find output impedance. So to find output impedance, we want to look at the circuit clearly. See, input is given as a current source. That means I want to consider as an open circuit, you know, right? So input is a current source. This is given. This is a transresistance. Input is a current source. So it will be open circuit. Open circuit, and here you have a feedback. This RF. So that means here there is no impact input. So here you have a dependent current source. Yes. Then here you have a RD. So I want to give some testing voltage in order to check it. What is the output impedance? Okay, so if you find like a output impedance, that is Vx by Ix. Generally I have written Vx by Ix. Right? So when you apply the KCL to this output node, to this each branch, okay, so here there is no impact because it is open circuited, the current source, so this will be impact of this VGS also considered to be 0 here, right? So here it is function with respect to the your testing voltage only, Vx only. So VGS also is going to be depend with respect to the Vx only, right? So when you write the equation, what you will be getting, that is Ix equal to this branch plus this branch, that is Vx by Rd plus GMVGS. So you can see here by applying the KCL. So this is your entering term and this is your leaving term. By using KCL, you let me take this is a node, and this is a entering term and this is a leaving term. This is a one, the term, this is a second term, right? So when you rearrange the equation, that is a Vx you take, manipulate the equation, Vx by Ix by Vx equal to 1 by Rd plus GMVGS. So this is the output impedance equation for the given transfer function given your transresistance amplifier. Suppose if you have a voltage like a voltage source, it will be a different concept, right? Here you need to find the impact of this your voltage also should be considered in the feedback part. Okay, that is our next problem we'll discuss in the next lecture. Okay, so just I want to say, if it is a voltage source, it's going to be a different, not to be a same situation. Okay, so you want to see the circuit and you want to further continue. Okay, so 1 by RD plus GMVGS. So substitute RD and GMVGS term, you will be getting 0.829, and you will be getting, that is the inverse of IXVX, that is a slope. So you will be getting 1.029. So when you want to find a transfer function, that is the reverse of the slope, that is Vx by Ix equal to 0.9718. So that is Vx by Ix equal to 1 divided by 1.029, we will be getting 0.9718. Okay, I hope you understood. Thank you.